Hey everyone! This week we're going to shift gears a little bit. So far for the past few weeks we've been talking about probative inductive arguments. And we're going to switch today a little bit. We're going to talk about what are called statistical inductive arguments. Now there's going to be a limit to how much we're really going to be able to talk about these because you'd have to do a lot of statistics. So we're going to have as our goal more just sort of getting fluency with understanding these different kinds of arguments, sort of understanding them when we see them and thinking about them in some better ways. So with all that said as preamble, let's get started. So let's just real fast review what we mean by a probative inductive argument, and then we can see how the statistical ones are a little bit different. So a probative inductive argument is one where the premises give you good reasons to believe that the conclusion is true, pending additional evidence, right? That we could sort of revise our opinion if we learn more about the world. Think about it, that what's going on in the probative inductive argument is that you're sort of trying to look at a whole, what does the evidence suggest is the case? Right? You're probably going to find some evidence that leans in one direction, other evidence that leans in a different direction. On the whole, looking at all the evidence taken together, what's the most rational thing for a person to believe? It's inductive because you could still be wrong. You could acquire new evidence that sort of causes you to recalculate, redecide sort of what the preponderance of evidence supports. A statistical inductive argument is a little bit different. The premises in a statistical inductive argument suggest that the conclusion has some very specific percent chance of being true. And so in that case, since they're a little bit closer to deductive arguments, actually, right? Because deductive arguments also suggest that the conclusion has some percent chance of being true. Namely, in a deductive argument, 100% chance, right? The conclusion is certainly true. In a statistical inductive argument, the conclusion is going to have some chance of being true, maybe 95, maybe 85, and that's what the premises will establish. How likely is it, in concrete statistical mathematical terms, that the conclusion is to actually be true? Additional evidence is only going to matter if it causes us to sort of recalculate the percentage. Okay, so the way we're going to evaluate these statistical arguments are by two broad criteria. We'll see that it sort of varies a little bit how they're precisely applied. But there's two broad criteria that we're going to look like. So other things being equal, first of all, the statistical inductive argument is stronger, the more likely the conclusion is to be true. If I tell you that some conclusion has a 95% chance of being true, that's just a stronger argument, at least if I'm right, than if their conclusion only has an 80% chance of being true. So let's say we're, for example, trying to decide how likely it is that someone is going to be able to run a mile. If there's a 95% chance she'll be able to run a mile, the conclusion is way more likely to be true than if there's only an 80% chance. If we calculated those numbers correctly, we should, think that the argument with a 95% chance is stronger than the one with only an 80% chance. And then if there's only a 45% chance that she's able to run a mile, yeah, then that's a pretty bad argument. That's a weak inductive argument. The second criteria that we're going to ask is basically, has the calculation been done properly? Have we calculated the percentage? It doesn't really matter if I say there's a 95% chance that someone will be able to run a mile if I didn't do my math right. If that 95% chance just really should be 60 or something. So those are the two questions we're going to ask. To really answer, especially the second question, you would have to do math, statistics, right? Statistics is sort of all about calculating these percentages in the right way. Since this isn't a statistics class, we're not going to go into all the sort of levels of mathematical detail that we could go into on this topic. We're just going to try to get some sort of broad fluency and understand what kinds of things are taking place in a couple different kinds of arguments. We're going to look at two kinds of statistical inductive arguments this week, what we're going to call statistical syllogisms and what we're going to call inductive generalizations. Alright, let's start with the statistical syllogisms. Now, this word syllogisms should sound familiar to it. We heard it earlier in the semester when we were looking at categorical syllogisms, a kind of deductive argument. So maybe let's real fast remind ourselves what that kind of argument looks like. So let's say we have an argument that all humans are mortal, Socrates is a human, therefore Socrates is mortal. The way that argument worked, it gave us sort of 100% certainty that the conclusion is true, because the all basically stands in for 100%, right? 100% of the humans are mortal things. If Socrates is in the human thing class, he's also in the mortal thing class. Statistical syllogisms work similarly, only they rely on some percentage less than 100%. So here would be an example of a statistical syllogism. 80% of the people in Athens are literate. Socrates is an Athenian, Therefore, Socrates is literate. And indeed, we can say precisely how likely is it that Socrates is literate? There is an 80% chance. So notice that the conclusion doesn't have to particularly say Socrates is most likely literate, or there's an 80% chance that Socrates is literate, though that's usually implied in some sense. The reason why you don't actually have to say that is because on the basis of the statistical syllogism, you should believe, if you had to take a guess, that Socrates is literate rather than that he's illiterate, right? There's a much higher chance that he's literate than illiterate based on the argument, so you should believe that he's literate, even though you recognize there's a chance you could get unlucky, and he's one of the 20% of people who aren't. Let's look at another example of statistical syllogism. So let's say 30% of humans can run a mile. Jill is a human, therefore Jill can run a mile. Indeed, how likely is it that Jill can run a mile? 30% chance. Immediately, you should suspect that something seems off with this version of statistical syllogism, right? I mean, if there's only a 30% chance that Jill indeed can run a mile, you should probably believe the opposite, right? You should believe that Jill won't run the mile. That has a much higher percent chance of being true. So if you had to guess again, it would be more rational to guess that she's not going to be able to on the basis of the argument than that she is. And so in this second case, we'll say that this is a bad statistical syllogism. It doesn't always have to be the case that you're dealing with a percentage. Oftentimes you will, but it doesn't have to be a literal number. Sometimes people will use statistical syllogisms and say things like a lot of people, or most people, almost all people. Those kinds of phrases are sort of standing in for some rough percentage sense, right? Maybe like almost all, maybe it's something like 95-ish%. And so you can run this a little bit less, mathematical with a something like that instead of a real percentage. We'll analyze it in the argument in the same basic way, though. All right, so what are our criteria going to be for analyzing these statistical syllogisms? There's going to be two. There's going to be two things you should look for. So first one, most obvious, assume that the percentages have been calculated correctly. Just start with that assumption. If they have been calculated correctly, a statistical syllogism is stronger, the more likely it is that the conclusion is true. Sort of exactly like you'd suspect, right? So we'd probably say if there's an 80% chance that Socrates is literate on the basis of our statistical syllogism, that's a pretty strong inductive argument. On the other hand, if Jill only has a 30% chance of being able to run a mile on the basis of the second statistical syllogism, we'd say that's a very weak statistical syllogism. And again, remember, these are relative notions. We could say that maybe if there was a 95% chance that Socrates was illiterate, that would be stronger than if he was 80, though perhaps both of them still are strong arguments. The second criteria is the one we're going to be a little bit more interested in. So the second criteria is what's called the rule of total evidence. According to the rule of total evidence, you have to use all of the available information available about the subject of the argument in calculating your percentage. So think of this rule of total evidence in effect as saying you have to have done the math right. We actually could indeed spend some time in statistics talking about precisely how to carry out this calculation. Well, in the end, we're not really going to worry about that. So let's look at some examples, sort of just common-sensey ones, to get some rough sense of how this rule of total evidence is operating. So let's start by looking at that second argument again. So what if I told you that Jill is a highly trained athlete of some sort? All right. I imagine that would change how you sort of felt about the argument, right? If we don't know anything at all about Jill, other than that she's a human being, then yeah, you probably should believe she has a 30% chance of running a mile, if that's how likely it is that any old average human being can run a mile. But a highly trained athlete isn't just any old human. There's information about Jill that's not being included in the calculation of how likely it is that she's able to run the mile. Right? Indeed, we suspect that there's a much higher percent chance that a highly trained athlete will be able to run a mile than the average person. Since that's not being taken into account by our calculation, this argument is violating the rule of total evidence. Similarly, to go back to the first case, let us say that I told you that Socrates was a poor peasant. Well, okay, you probably should suspect that the percent chance that a poor Athenian peasant is literate is probably way lower than just the chance in general that some Athenian is going to be literate. And so again, you would suspect that this argument has violated the rule of total evidence. The percent wasn't calculated right. There wasn't, percentage wasn't calculated with a high enough chance. Again, let's go even further. Let's say, though, that Socrates indeed was a poor Athenian peasant. Let's say that in addition, I told you that Socrates is one of the foremost intellectual thinkers in Athens. Okay, again, that again suggests that there's some evidence that's being lacking, because I imagine the percent chance of people who are Athenian citizens, who are poor peasants, and the foremost intellectual thinkers in the city That's probably way higher, right, than 80%. And so again, in both of those cases, the percentage hasn't been calculated using all the available information. We violated the rule of total evidence. We're going to say that any argument that violates the rule of total evidence commits the fallacy of incomplete evidence. And any argument that commits this fallacy, we're going to reject it regardless of how high the percentage is, because if the percentage hasn't been calculated right, doesn't really mean much. There's no reason to really take it that seriously. Alright, that'll do it for this first part of the video this week. The subsequent video, we're going to look at inductive generalizations and spend the entirety of that video looking at those. A bit more to say there. Alright, talk to you later. Bye!